We're going to introduce the topics of kinetics, chemical kinetics, first showing how relevant the study of kinetic is, not only in chemistry, but in many other areas. In general, kinetics implies the change with time, the rate or the speed at which this change takes place, and it does not only apply to chemistry. Any change that you may think of, like well, in this case, if it were a reaction, the reactants becoming products, it can be expressed as in different fashions. We will have time to express it with mathematical forms, but the simplest of them is how much the concentration of reactants change with time, and that is proportional to the initial amount. That leads to something that you may have heard about, which is called exponential decay. And exponential decay is a law that is present in many other areas other than chemistry. So for example, the effect of a drug in a human body decays with time because this specific drug gets metabolized into products in a similar fashion than reactants become product. This field of study of how drugs change with time or how they are metabolized is called pharmacokinetics. And so the tools that we will learn in chemical kinetics here are potentially applicable also to pharmacokinetics. Other areas that the tools that we're learning in here will also be applicable is, for example, radioactivity. The rate at which radioactive nuclei decay follows what we call a first order kinetics, or in other words, follows an exponential decay. Other applications, the rate at which a body loses heat with its surroundings, provided that the surroundings are at a lower temperature, also follows an exponential decay. The same way for sound. The rate at which the loudness and the spectral content of the sound decays with time follows an exponential decay. So there are many instances, even the fluorescence, or if you will, even the human eye, the way human eye is impacted by light, the way it stops being excited, that follows also an exponential decay. So we will learn a specific set of laws and tools that are potentially applicable to a very wide variety of topics. First of all, if we are concerned about chemical reactions, we want to understand first what factors that we can control is going to affect the rate of reactions. For example, one first needs to accept that, and this is something we will talk about in the next video in the molecular kinetic theory, is that not all molecules in a specific container are at the same travel at the same speed. Okay, but what's important is that for a reaction to take place, what needs to happen is two things. Molecules need to collide, and molecules need to collide with the right orientation. So in here you see that it says no reaction, not because they did not collide, it's because they did not collide with the right orientation. So whatever factors increase the chances of collision and right orientation, it will increase the rate of that specific reaction. So for example, temperature. Well, temperature is related to the speed of gases and liquids and solids. So the higher the temperature, the higher number of collisions. Therefore, the higher the chances are that that collision leads to products. Therefore, the higher the temperature, the higher the rate of the reaction. Concentration. Also, the higher the concentration or density, it implies that the higher the chances of collision. Again, therefore, it will also, a higher concentration, it will also increase the rate of the reaction. Notice, though, that what matters is the concentration, not the absolute size of the container. Having a big container or a small container, of course, if you increase the container without having to increase the number of moles, that will lead to a lower concentration, and that would decrease the rate. So what's really relevant, it's not the size where your um, the size of the container where the reaction takes place. What matters is the concentration. Also, the difference between solid, liquid, and gas is that gas, as you all know, moves faster and it intimately mixes with each other much better than solid, for example. So as you go from solid to liquid to gas, the rate of the reaction should increase because gas moves faster, therefore there's more collisions, and so it increases the chance of having a collision that leads to products. Okay, a reaction between solids will be fairly slow compared to its counterpart in gas. Okay, the same for catalyst. A catalyst is a substance that changes a little bit the mechanism for which the reactants become products. Typically, it should speed up the reaction. Think of enzymes, for example. The higher the number of the higher the concentration of the catalyst, the higher the rate. Ionic strength is something, it's a concept that it will deserve its own video, so bear with me, we are not talking about it yet, but we are saying that the ionic strength will depend on, the effect of the ionic strength on rate will depend, it will depend on the charges of the reactants, So let's leave it there, and we'll definitely talk more about that. But whatever we study, we have to keep in mind all these factors. There will be quantitative ways to study these factors, but definitely these should make sense at this point.